Hello, everyone. Can everyone hear me okay? All right. And I hope everyone's adjusting to the dark. Uh, as Sophia mentioned, my name is Mark. My clicker is not working. She didn't mention that, but I mentioned that. My name is Mark. I'm a graduate student here at the University of Toronto. And today I'm going to talk to you about one of my favorite pieces of physics, which is tides. And you may be wondering, what have tides got to do with this galaxy on the screen? And we'll get to that at the end, I promise. So first of all, if I mention the word tides, if I turn on my clicker, maybe that would help. If I mention the word tides, one of the first things you may think of is the ocean. And so let's start with a day at the beach. So say, your family is going out to the beach. If your family was anything like mine, your dad wants to get there at 7 a.m. Instead, maybe you roll up at 10 a.m. And you put your umbrella down, you put your blanket down, you have a nice little day, you go into the water, you go to the boardwalk, you come back to your blanket, you lay down, you take a nap. Sometime in the mid-afternoon, the water is up at your feet. And you're like, that's weird. I'm pretty sure I put the umbrella far enough away from the water that this shouldn't be happening. Maybe you have a nice rest of your day, you go home, you come back later that night, and you see that the water's back down, and then maybe you try to catch the sunrise the next day. So early morning, before the sun has risen, you come back and the water's back up to where your umbrella was the day before. And what you've just observed, well, first of all, you've just conducted an experiment. Congratulations, you've done science. So those 4 measurements you took, at 10 a.m. one day, the tide was low, the shoreline was low on the beach, then it was high, low again, and high again. You've done experimental astrophysics. Congrats. These changes, what we call the tides of Earth's oceans, the gist of this talk is that these are just one example of a broader class of physics known as tidal physics. And it's a very close to Earth example because it happens on the Earth. But as we'll see, tidal physics plays a role in shaping systems all across the universe. And so that's the topic of today's talk. So today's journey, we're going to start with the Earth. We're going to learn a little bit about what drives the tides and also how the tides are impacting the moon. Then we're going to move a little ways away in this visual of our galaxy made by NASA from the top down. We're starting right near the sun, that's point 1. Then we'll move over to point 2 and witness the slow demise of a planet. And then we'll move right to the center of the galaxy, point 3. And we'll talk about an incredibly heavy slingshot that lives there. And again, all of these topics are going to have the same sort of physics at the core of them. So first, the Earth and her fleeing moon. So just to get ourselves situated, as you may know, we live on a planet. That planet orbits a star. That star we call our sun. This is not even close to scale, but a diagram showing the Earth orbiting around the sun. It takes us 1 year to get around the sun. That's how we define the year. The Earth also rotates. It takes us 1 day to spin around fully 1 time. And around the Earth, of course, we have a moon. You've all seen the moon in the night sky, I hope. And we'll be talking a lot about the moon throughout this talk. So to zoom in on that, the Earth and the moon, always relevant to our lives. But maybe recently you heard on the news that we went back to the moon, or we went back beyond the moon with the Artemis 2 spacecraft, which was pretty neat. This little diagram here is just showing the trajectory that spacecraft took to get all the way out to the other side of the moon and come back. And of course, they took pictures. And so if they, at that point in their trajectory, took a picture, this is what they saw. So this is a real image of the Earth on the right of your screen, viewed from the moon. And the moon looks way bigger. In reality, the moon is about a quarter the size of the Earth. But because of the vastness of space, because there's so much distance between the Earth and the Earth looks frankly pretty small from this vantage point. So this is just to sort of, again, situate ourselves and get a sense of the scales that we're talking about here. These are huge distances between the moon and the Earth. So a lot of tides, actually all of tides, has to do with gravity. Gravity is one of the 4 fundamental forces that shape our universe. Newton figured it out back in the 1600s. And the important things about gravity, for the purpose of this talk, is that everything with mass attracts everything else. The Earth has mass, and so it attracts us. It pulls us down toward the Earth. The moon has mass, so the moon pulls the Earth toward the moon. Same goes the other way. The Earth is always pulling the moon toward it. And the other important thing about gravity is that the closer you are to something, the stronger its attractive force. So if we were all the way out by the moon, we would barely feel the gravity of the Earth. But because we're standing right on top of the Earth, we can jump maybe a meter high, but can't get much further than that without being pulled back down by that gravitational attraction. And the beautiful thing about gravity is that it always works the same way. No matter what two bodies you have in space, no matter what two masses you're talking about, they are always going to attract each other. And that attraction is always going to be strongest the closer, it's going to be strongest when you are closest to each other. And so gravity is going to come up a lot in this talk, in a lot of different contexts, but just throughout it, remember that no matter what the two bodies are, they're always pulling toward each other. So the pull of the moon is stronger when you're closer to it, right? That's that second major point about gravity. So that means that the different sides of the Earth, the different parts of the Earth, feel the strength of the moon's pull at different strengths. So the side of the Earth that's closest to the moon is going to feel the strongest pull from it. The center of the Earth is going to feel sort of a middling level of pull from the moon. And the far side of the Earth, as viewed from the moon, is going to feel the weakest pull. Again, this is just from gravity. The further you are from something, the weaker its pull. And so the result of this is that the moon is actually going to deform the Earth. The moon is going to stretch the Earth toward it. So the Earth would like to be a perfect sphere. Just under its own self-gravity, it would like to be a perfect sphere. But because of the presence of the moon is constantly pulling the Earth into this sort of oblate, ellipsoidal non-sphere. And of course, the Earth is going to also deform the moon in just the opposite way. It's also pulling strongest on the close side of the moon and less strong as you get to the other side of the moon. But for the purpose of this talk, the interesting thing is that the moon deforms the Earth. So the moon causes this bulge to be raised on the Earth. Now, the other thing that has to be true to give us tides is that the Earth spins. So remember at the start, I said one time around Earth's orbit, that's a year. One revolution, one spin of the planet, that's a day. Does anyone know how long it takes the moon to go around the Earth? I think I heard 28 days, which is the right answer. So the phases of the moon from new moon to new moon takes 28 days. And that's because one orbit of the moon around the Earth takes 28 days. So the spin of the Earth is much faster than the motion of the moon. The Earth spins 28 times in the time that it takes the moon to go once around the Earth. And so the result is that as we spin, if you imagine just a person standing maybe right there, as the Earth spins, that person is going to travel under this bulge and then back to this shallower region, and then under the bulge again, and then back to the shallower region. And the moon is barely going to have moved because, again, it takes 28 days for the moon to get all the way around. It only takes 1 day for the Earth to spin. So we can animate this with this nice little visual from NASA. So the bulge that the moon causes on the Earth is always pointing in one direction. It's always pointing right at the moon. And then as the Earth spins, we travel under the bulges. And that is what gives us the tides. So if we go back to our initial picture, our day at the beach. So imagine we arrive mid-morning and our umbrella is our location on the Earth. And we're sort of facing away from the moon. And we're sort of in this low tide region where the bulge is actually sort of slightly compressed. It's not pulled out in that direction, but it's compressed in that direction. And then about 6 hours later, the Earth has spun a quarter of the way around, and suddenly we're experiencing a high tide. The shoreline has risen just because we've moved around into this region of the Earth that's stretched, that's elongated by the moon's tidal gravity. And we keep rotating, rotate 6 more hours, and we're on the opposite side and experiencing a low tide again. And then again, the next day, before dawn the next day, we get back to a point where we're under the bulge of the moon once again. And so these two effects give us the tides of the ocean, right? The next morning, if we stuck around till mid-morning, we would experience a low tide again. So again, the moon gives us this bulge on the Earth And then the ocean around us appears to rise and fall simply because we're moving under that bulge over the course of the day as the Earth rotates. So that's very simply how we have tides on the Earth. And the crazy thing that I learned while preparing this talk is that the Greeks knew this. Well, the Greeks didn't know about gravity, but the Greeks were able to look up at the moon and look at the changes of the ocean level. And they were able to say that when the moon rises above the horizon, to the extent of a zodiacal sign, so 30 degrees above the horizon, the sea begins to swell. So the shoreline raises up and perceptibly invades the land until the moon is at its meridian, which is right overhead. So the Greeks recognized that as the moon went across the sky, as we sort of turned to face the moon, the sea level also rose. They were identifying the relationship between the moon and the tides, which I think is pretty neat. The oldest surviving writing of this was from just 23 years after the year zero. And I mentioned that gravity is what's giving us the tides. Gravity is what's giving us that bulge of the Earth. Gravity wasn't discovered for another 1,600 years by this guy, Isaac Newton. And in his Principia, which is where he wrote down his theory of gravity and suggested that everything that has mass attracts everything else, he drew this diagram. And this diagram is exactly the same as the diagram I just showed you. So what he's showing here, the L is our luna, our moon. And this sort of ellipse is representing the Earth, which is deformed by the moon's gravity and stretched toward it. So again, the Greeks recognized that the moon was related to the tides, but they didn't have the why. They didn't know that there was a cause behind the connection. They could just say there was a correlation between the two. And then it wasn't until Newton came around to really make this secure and really say, actually, it's because of gravity. I mean, personally, I think my diagram is a little bit better, but I guess if you're not first, you're last with this sort of thing. Right, and now you have learned this in less than 20 minutes. I think it's been 15 minutes since the start of this talk. So congratulations to you. You've learned tidal physics in all of 20 minutes. Yeah, give yourselves a round of applause. But why would an astrophysicist ever think about tides? So this is an AstroTour. I am getting my PhD in astronomy. Why would I, in thinking about space, really care about these things that seem to be impacting the Earth? Tides seem to be an Earth-based phenomenon. So as I mentioned, these tidal bulges that are raised by things like the moon, they actually change the motion of the things that raise them. So the tidal bulge that the moon raises on the Earth changes the motion of the moon around the Earth. And we're going to talk about what exactly this means right now. What this means is that the moon is moving away from the Earth. Now, don't be alarmed. But the way we know this, I think it's pretty neat. We shoot lasers at the moon. I'm dead serious. We shoot lasers at the moon, and they bounce off these tiny little reflectors that we left on the moon when we went there back in the 60s. These are less than a square meter. And we can shoot lasers precisely enough from the Earth to actually bounce off these reflectors. And then the lasers come back to the Earth. And we can actually measure the time that it takes for that laser pulse to travel from the Earth to the moon and then back to the Earth. And that tells us how far away the moon is. And then people with a brain that's much more wired for precision than mine go through and do very detailed modeling and make tables that look like this. And end up getting results that are in this column that you don't need to read because that's way too many numbers. But the important thing is that these results are reported in millimeters per year. So this column is telling us how quickly the moon is moving away from us. And we're measuring it in millimeters per year. So it's not moving away from us that fast. And in fact, it's moving away at a whopping 3.8 centimeters per year. So this is interesting, and this is related to tides, and we'll get to that in a moment. But first I guess I already talked about my dad in this talk, but I'm going to mention him again. He's turning 60 this year, which is great for him. So when he was born, this is what the moon might have looked like in the night sky. And you know, like as things move further away from you, they become smaller in your vision. Like someone at the back of the room looks much smaller to me than someone right here, even if they were the same size. And so 60 years later, my dad has lived a wonderful life, and now he gets to see the moon, and it looks like this. that was a lie. I didn't actually change it because it's only 0.06% smaller. So it has barely changed at all. The distance to the moon is 38 billion centimeters, so 3.8 billion centimeters per year is a very tiny amount. But it's, again, something that we can measure, and I think that's really neat. But if we waited 1 billion years, then the moon would look about 10% smaller. That's 1 billion years. That's about 1/5 of the time that the Earth has been around, that the sun has been around, and about 1/5 of the way through the rest of the sun's lifetime, about 1/10 of the age of the universe. So none of us will be around, of course, in 1 billion years to see it be 10% smaller, but if we were, we would no longer be able to see solar eclipses because the moon would be too small on the sky to completely block out the sun. And that's a real shame for people around 1 billion years from now. So anyway, that's a long digression. Why is the moon moving away from the Earth? Well, so it has to do with a little visual lie that I've been telling, which is that this bulge points directly toward the moon. So I've drawn this white dashed line here that connects the center of the Earth to the moon. And I've been showing you this bulge as if it were pointing right along this white line. And in fact, this is not true. And it's not true because the Earth rotates. And as the Earth rotates, it sort of pushes that bulge forward relative to the moon. And the reason it does this is that the rotation is much faster than the motion of the moon. So the moon is just hanging out here, and the Earth is trying to move forward. And there's a little bit of friction between the bulge that's being raised by the moon and the Earth's rotation. And so the result is that this bulge gets slightly misaligned by some very small angle. I'm way dramatizing it here. But the bulge gets slightly misaligned. And now I'm going to draw some arrows. And they might, oh, never mind. I'm not going to draw some arrows. This misalignment, I want to point out, is constant. So even though the Earth is rotating, this slight angle between the direction of the bulge and the direction to the moon, that angle isn't changing. So it's not like the bulge is now rotating. It's just sort of at this fixed angle a little bit forward of the moon. So now I'm going to draw some arrows. So if we just considered sort of the bulk gravity of the Earth, then the moon would be attracted right toward the center of the Earth. But now we've got this little bit of mass that's pulled away from the center of the Earth. And so that little bit of mass is also going to have some attraction, or induce some attraction. So the moon is going to be attracted to that bulge that's leading it in its orbit. And the result of this is that the moon is going to be sort of pulled along in its orbit. It's going to be sped up. And when you speed something up, this is something that is not at all intuitive, and there's no reason that you should know this. When you give something a little boost during an orbit, its orbit is going to grow. And so it's this misalignment and the fact that the moon is attracted to this little bulge that leads it. And again, this is a microscopic difference. But it's this misalignment that causes the moon to speed up and causes its orbit to grow over time. And again, its orbit is only growing 4 centimeters per year. So a tiny, tiny amount. But again, an amount that we can measure. And I think that's really neat. So this is only happening because the Earth is rotating faster than the moon is orbiting. So what would happen if the Earth spun more slowly? If the Earth spun slower than the moon, then this bulge would instead lag behind the moon. The line connecting the center of the Earth to the moon would be in front of the line of the bulge. So if we draw the same arrows, the bulk of the gravity is pointing straight at the center of the Earth, but then there's this little component that's pointing behind the center of the Earth. And so that's going to slow the moon down on its orbit. And we said when you speed something up on an orbit, it grows. When you slow something down on an orbit, it tends to shrink. And this will come in handy in our next stop in our journey, I promise. And then if the Earth's spin was perfectly synchronized with the moon, then there would be no extra force. It would just be the force pointing directly along the line connecting the center of the Earth to the moon, and there would be no change in the moon's orbit. And so this, people often say in science that you shouldn't talk about like wanting something, or shouldn't talk about the universe wanting to be a certain way, because the universe, of course, is cold and heartless and has no desires of its own. It's just sort of following the laws of gravity and physics. But one way you can think of tides is that they always want to reach this state of synchronicity, of synchronization. They want to reach the state where the spins of the two bodies are the same, happen at the same time as the orbit of the two bodies. So the Earth-Moon system wants to get to a state where the spin of the Earth is the same, takes the same amount of time as one orbit of the Moon. And that will happen in 50 billion years. But the universe probably won't be around in 50 billion years to see it happen, so it's a real shame. Right. So to recap very broadly, this big first section, which I promise is where I hid all of the annoying physics. Tides change orbits. And so to an astrophysicist, tides are very important because tides are going to change how these celestial bodies are moving around each other. And that's all I'm really interested in, is how these celestial bodies are moving around each other. So the Moon is running away from the Earth because the Earth is spinning a lot faster than the Moon is moving. And again, we want to get to that state where the motion of the Moon and the spin of the Earth are perfectly synchronized. And if the Earth spun very slowly, the Moon would instead come toward us. So now we're going to leave the Earth-Moon system. We're going to move on to our next stop. This is the WASP-12 system, a very creatively named system. Astronomers are, in general, creative people. And so we name our stars after the surveys that discovered them. So this was the WASP survey, and it was the 12th star discovered in the WASP survey, so it's WASP-12. And we could not be more creative than that. So WASP-12 is the star, and this is a planet. This is a planet that is about the size of Jupiter, the biggest planet in our solar system. And frankly, it's way too close to its star. And I'll tell you what way too close means. But first, I'll note that it's called WASP-12b, because this would be WASP-12a, but we don't put the A on it because the A is obvious. It's just the first one. And this one is B. So there's no WASP-12a. It's WASP-12 and WASP-12b. And WASP-12b is a planet that's way too close to its star. Now, what do I mean by way too close? Well, so to go back to this diagram that I showed at the start, that I said was completely not to scale, I'm now going to scale down the Sun and the Earth to be appropriately sized relative to their distance, so that you can see just what that should look like. Okay, perfect. You guys see, there's the Sun. The Earth may be somewhere there. It might be smaller than a pixel, so it might not be showing up. So let's enhance. Let's zoom in. Okay, perfect. All right. There's the Sun. And the reason that I need to show you this scale is to show you just how close to its star WASP-12b is. If I showed you WASP-12b's orbit on here, you wouldn't believe it. It's right about there. So WASP-12b, that was a great reaction. Thanks, guys. Holy cow. Wow, what an audience. I'm feeling a rush. Maybe I should go into performances. So, okay. Anyway, so WASP-12b has an orbit that's 2% the size of Earth's orbit. It's frankly way too close to its star. So if we enhance again, if we zoom in, this orbit is now entirely to scale. So that is like the size of WASP-12, and that is the size of WASP-12b, and that is the distance they are from each other. That's crazy close. Nothing in our solar system comes even close to the Sun relative to WASP-12b's distance to WASP-12. And because it's so close, WASP-12b is going to raise tides on its star. And in fact, this system is going to be like our slow rotating Earth case. So if we draw that line between the center of WASP-12 and the location of WASP-12b, we would get a bulge that lags behind that line. So the misalignment is backwards. And so if we draw our little arrows from before, we get a force that is backwards on the orbit of WASP-12b. And what did we learn from the Earth-Moon system? We learned that I just clicked backwards. What did we learn from the Earth-Moon system? We learned that when you put a force backwards along the course of an orbit, what you get is orbital decay. So the orbit shrinks over time. So because this system is like the slow rotating Earth case, WASP-12b is actually shrinking its separation between it and its star. It's spiraling inward toward its star, which is tough. I mean, it's already pretty close. It can't get much closer, can it? It can't. So scientists have actually observed this orbital decay. I keep clicking back, sorry. Scientists have actually observed this. So the size of an orbit corresponds to how long it takes you to get around it. The smaller an orbit is, the faster you get around it. The bigger an orbit is, the slower you get around it. And so we can look at the time that it takes WASP-12 to go around its orbit, and we can ask, what's the change in that time? So we measured it back in, I think, the early 2010s, actually maybe like 2008, 2009. It was first measured back in 08, 09, and we determined how long it took WASP-12b to go once around its orbit. And then we've been measuring it ever since. And for the 10 years after that, we saw this gradual decay. And this orbital change is measured in minutes. So again, this is a pretty small change. The influence of tides, generally pretty small, but measurable. And so we can measure how rapidly this decay is actually happening. And the really interesting thing about WASP-12b is that this is the only planet that we've seen this happening in. And you might think, well, is that because WASP-12b is, again, ridiculously close to its star and no planet should ever be there? But in fact, many planets are that close to their star. About 1% of stars like the sun in our galaxy are estimated to have a planet roughly the size of WASP-12b and roughly as close to its star as WASP-12b is. But it's the only one where we actually measure this. And so there's a decent reason for this. And that's that a planet can't keep spiraling in forever. As it spirals in, the tides are going to get stronger. Both the tides that it raises on the star, and so its in spiral is going to speed up because of that, but also the tides that the star raises on the planet. So remember, I mentioned at the start that the moon raises bulges on the Earth, and the Earth also raises bulges on the moon, but we weren't going to talk about that for now. Now we're talking about that. WASP-12 raises tides on WASP-12b. And so as WASP-12b spirals inwards, those tides are going to get stronger. And eventually they're going to get so strong that the planet is going to be ripped apart by this tidal force from WASP-12. It's going to cross what's known as the tidal disruption radius. So there's some distance that you can come from an object where you're way too close. Like you're intruding, you're not welcome anymore, and you're going to get torn apart by this tidal force, this difference in gravity from one side of the planet to the other. And eventually here means the next few million years, which may be a lot of time in Earth time, but the universe has been around for 10 billion years. And so most of the planets that we're looking at, most of the stars that we're looking at are billions of years old. And so for something to happen in just a million years, that's like that. Like in the span of this talk, I shouldn't have brought that up because I can't do the conversion. But in the span of this talk, that would be a tiny amount of time. That's 1/1000th of the age of a lot of these systems. And so to actually be able to catch a system, to be able to observe a system that's undergoing this decay, this process that's only going to take a few million years, is pretty remarkable. And we're pretty fortunate to have detected WASP-12b. It's one of the first examples, that plot I showed is one of the first examples of where we've actually been able to constrain how long this process should take. And one of the things that I do in my thesis research is I think about pairs of stars that are orbiting each other. So just like this planet orbits a star and that orbit is frankly much too small, there are also pairs of stars that have orbits that are much too small around each other. And these stars should also gradually spiral in toward each other. And so one of the things that I do in my thesis is I try to think about how long that should take for those stars, and I try to use observations of these very close together stars to constrain how long this process should take. But WASP-12b is one of the very first examples that we have where we have a direct measurement of how long this process takes. And that's pretty neat. And in fact, this disruption may already sort of be underway. If you were really keen-eyed when I showed this illustration earlier, you might have noticed these like strands of apparently smoke. These are meant to represent gas coming off of the planet. So there's some evidence when we look at WASP-12 and WASP-12b that there's already gas coming off of this planet, coming off of this Jupiter, being stripped and deposited onto its star. So to recapitulate some of the key points, some planets are doomed by tides. And this doom process occurs really rapidly, so we only see a very few of them. but WASP-12b is our prototypical example. It's a Jupiter-sized planet. It's way too close to its star, and it's falling ever closer due to tidal decay. So that's a tragedy, frankly. Now we're going to move on to what some may call a bigger tragedy. So this is an incredibly heavy slingshot in the center of the galaxy. And people who have seen previous AstroTours may know that at the center of the galaxy, there's something that looks like that. That is a supermassive black hole. Its name is Sagittarius A star, or Sag A star. Again, very creative namers, astronomers. Sagittarius is the constellation that this object appears in if we look at it from our position. Actually, I don't know the naming history of Sagittarius A star, but we're not very creative. The star means X-ray. So yeah, Sagittarius A star is a supermassive black hole. And by supermassive, I mean 4 million times the mass of the sun. So this is a really, really, really heavy object. And in fact, all of the mass is concentrated right at the dead center of Sagittarius A star. And what we're seeing is just some gas that's swirling around it, that's letting off light because it's being caused to move at very high speeds by being so close to this supermassive object. And to put this image into perspective a little bit, some people say it looks blurry. It's in fact the most precise, the most high-resolution picture ever taken. So WASP-12b's orbit would be sort of right at the center of it. This whole image is about a third of the size of Earth's orbit. And we took this picture from 250 million billion kilometers away. So this is a pretty impressive feat of science that we were able to take this picture of this supermassive black hole. Now, why am I talking about this? Well, in the center of the galaxy, there are also occasionally those pairs of stars that I mentioned last time. So stars that are orbiting each other. They're common throughout the universe. About half of stars like our sun have a companion. The sun is sort of rare in that it doesn't have a companion. And in the one of the key aspects of my thesis is modeling the evolution of these pairs of stars near Sagittarius A star. And one thing that, so by near, I mean that these stars, while they orbit each other, the whole pair of them, which is known as a binary, is moving around Sagittarius A star in an orbit. And this orbit looks sort of different to the rest of the ones that I've been showing. I've been showing you very circular orbits. This orbit is very eccentric, very elliptical, very elongated. It's stretched out rather than being a perfect circle. And that's sort of typical of orbits around a supermassive black hole. And now these stars, this is a talk about tides, and these stars are subject to tidal forces. The star that's closer to Sagittarius A star is going to feel a stronger pull from the massive black hole. And the star that's further from it, even if it's a small little distance further, is going to feel a weaker pull. You've seen a diagram like this before when we were talking about the Earth and the Moon. It's the same exact physics that caused the moon to be, or caused the Earth to be stretched toward the moon, is going to cause this binary to be stretched towards Sagittarius A star. And just like in the WASP-12b system, where there was this tidal disruption radius, this separation from the central body, where we couldn't get any closer or we would be torn apart by the tidal force of that central body, so too is there a tidal disruption radius around Sagittarius A star. And if this binary comes too close to Sagittarius A star, well, it's going to be destroyed. The two stars are going to drift further from each other due to the unequal gravity that they're feeling from the supermassive black hole. Eventually, one of them is going to get flung off into space. Whee! You shouldn't be laughing. This is tragic. I'm pretty sure I was pretty clear about that. So these stars, which are coexisting perfectly happily, they were best friends, maybe even lovers. They were torn apart by the tidal forces of this supermassive black hole. Yeah, that's sad, but it's pretty neat for astronomers, and we can model it. So I'm going to show you an animation right now. This is a direct simulation of a binary, so two stars going around each other, and that circle is showing sort of the scale and the circularness of the orbit. And we're coming close to Sagittarius. Say, oh, you might have missed it. So this is a process that happens really quickly, and I'll let this loop a couple times, but you can watch in the top left, that's a ticker showing the number of days since the start of the simulation. In the bottom right, it's showing how wide this window is. We're currently a bit over 1,000 times the distance between the Earth and the Sun. There are a few different white lines that I'm showing. So Neptune's orbit around the Sun is shown down at the bottom. And then this big ellipse is the orbit of SO2, which is the star that's closest to Sagittarius A star that we've been able to observe. I'll play that again. Yeah. So again, it's a blink and you'll miss it sort of situation, and I'll show a slow motion version in a second. But as these two stars come close, they start to feel the tidal gravity of Sagittarius A star more and more, and then they're torn apart from each other. And you'll notice that this blue one is going to itself enter a nice little orbit around Sagittarius A star. It's going to be a very elliptical orbit. But this red one, gone forever. Like, hasta la vista. This red star is flying away, never to return to Sagittarius A star. And it's flying away at thousands of kilometers a second. That would cross North America, if it were smaller than the size of North America, in less than a second. And we actually observe stars like this. And I'll talk about that in a second. But first, I'll give you a little, ooh, don't want to go. Okay, this is an instant replay. So here we're showing a slowed down version of the same thing. And the shape of this white circle is reflective of the shape of the orbit. And so the orbit starts off very circular, the orbit of these two stars. And it's going to get stretched in just the same way we were saying that the planets are getting stretched by the tidal force. And then eventually it's going to get so big and it's just going to disappear entirely. And that's when these two stars get uncoupled from each other. One of them gets flung off across the universe. The other keeps going around Sagittarius A star. So I think this animation is pretty neat. I think this process is tragic, and no one should be laughing about it. But it's a really neat piece of physics. Again, this just comes from the same tidal physics that we've been discussing for this whole 40 minutes now. You learned this 20 minutes ago. This is a really extreme example of tidal physics, and it's known as the Hills mechanism after this guy Hills, who figured it out back in 1988. And this is what gives us the fastest stars in the galaxy. I mentioned that red star was moving at like 4,000 kilometers a second. For reference, the sun, which is a pretty average star in our galaxy, moves at about 200 kilometers a second. So that's like 20 times faster than the motion of the sun. One such star, in fact, the only star that we can confidently say was ejected from the center of the galaxy by this mechanism, is known as S5 HVS1. Again, so creative. S5, the survey name. There are 5 words that all start with S in the survey title. I don't remember them all. But S5 is the short name of the survey. It's led by a professor here at the University of Toronto, Ting Li, or I guess it was led by her. And then HVS1, hypervelocity star 1. It's the first one that they found with S5. Creative folks. So S5 HVS1 is moving at 6 million kilometers a second. 6 million kilometers an hour. 6 million kilometers a second would be crazy. But again, the typical stars in our galaxy are moving at like 100,000 kilometers an hour. And it's moving directly away from the galactic center. It was probably kicked out by this Hills mechanism, by this example of tidal physics. And so one of the other components of my thesis, some work that I'm hoping to publish pretty soon, is on basically the reason why, I think it's the reason why S5 HVS1 was kicked out when it was kicked out. It was sent off about 6 million years ago. There are also some stars in the center of the galaxy around Sagittarius A star that are about 6 million years old. And some may say that's a coincidence, but I think not. And I'm pretty confident that it's not. And I'm going to, I won't get into that in this talk because it doesn't have to do with tides, but it's a very fun piece of physics. And I'm very happy to have had a chance to model something as cool as S5 HVS1. So again, to recap, tidal interactions with Sagittarius A star, binaries coming too close to it and getting torn apart by its tidal forces, produce the fastest known stars in the universe. Well, in the galaxy, and those are the only stars that we're able to really cleanly identify. So today's journey, we've started off here. We've started with the Earth. We've learned about tides on the Earth and what causes them. It's the moon. And then we've learned about why the moon is moving away from the Earth. It's tides. We've talked about the slow demise of a planet, why WASP-12b is spiraling inward toward its host star, WASP-12. Shockingly, it's also tides. And we've talked about an incredibly heavy slingshot, this supermassive black hole that sits at the center of our galaxy and that occasionally, rips apart two stars that comprise a binary, flings one of them off at remarkable speeds, and keeps the other one cruelly from its friend. And so now I feel I owe it to you to end on this, which is my title slide. This is a picture of a galaxy. This is known as the tadpole galaxy. It's known as the tadpole galaxy because it's got this long tail. Would you believe it if I told you that this tail is caused by tides? You might believe it because that's all I've been talking about. So a few 100 million years ago, another galaxy passed between us and the tadpole. And it passed close enough to the tadpole that the tidal force from the gravity of this other galaxy was enough to pull off some of the gas and stars that made up the tadpole. So a galaxy went from over here, went wee, and while it went wee, it's the difference in gravity from one side of the tadpole to the other meant that all this gas got pulled off. And I think that's a remarkable example of tides. I think what's really beautiful about this is these little clumps of blue light down at the bottom of this streamer of gas. These are stars that are forming. These are young stars that are being born out of this gas, and they wouldn't have otherwise been born. If this gas had not been flung off by this tidal interaction with another galaxy, these stars likely wouldn't have formed. I mean, maybe there are other worlds around those stars. Maybe there are WASP-12b's that are eventually going to be doomed. Maybe there are worlds where there are aliens who may be able to communicate. I mean, I'm getting a little ahead of myself there, but I just think it's really remarkable that something that gives us, the rise and fall of the oceans on Earth is the same exact physics that gives us something like this, that can give life to whole new stars, whole new worlds. So that's why this talk is titled Tides, because I just think they're neat. And with that, thanks so much for listening, and have a great night.
Thank you, Mark, for the amazing talk. We have some time for questions. Does anybody in the audience have a question?
Yeah.
Up there.
Thank you for your talk. It was really fascinating. Thanks. I just wondered if, just from high school, like physics, if like spring and neap tides impact what's going on with the moon. Does it change anything in terms of how fast the moon is going away from us? Or, how does it change that? And then the other question was, with WASP-B, 12b, the thing that's deforming is the gas. Once that gas is all gone, does that then change the sort of physics of what's happening to that as well? Thanks.
Those are fantastic questions. So the first one, for those who might not have heard, had to do with spring and neap tides. And spring and neap tides are a variation of that sort of rise and fall that I was showing, that have to do with the fact that the sun is also a massive body and also exerting gravity on the Earth, and is also causing a tidal force, a tidal bulge to arise on the Earth. And so when the sun and the moon are aligned in the sky, when they both appear in one direction from our line of sight, then the tidal bulge that gets raised on the Earth is much larger than when they're in different directions. So like if I was looking out that way and I saw the sun, and that way and I saw the moon, then the tides that I would feel would be weaker than if the sun and the moon were both in that direction. And the question was whether that changes the speed with which the moon moves away from us. And I would say that it does in the moment, but also that we go through these spring. So I would say that spring tides, which are when the sun and moon are aligned, you would probably get the fastest evolution then, and then you'd get slower evolution during neap tides. But because we go through phases of spring and neap tides every 28 days, that effect sort of averages out. And so what we measure, that 3.8 centimeters per year, that's just sort of an average effect over the course of the year. And so overall, it doesn't change the picture of what we're looking at, but in the moment, I would say it probably does change how quickly the moon is receding or coming toward us. That's a great question. And then your second question was on WASP-12b, and it was about, once all the gas is stripped. So Jupiter and Jupiter-like planets are made entirely of gas. So unlike the Earth, which is mostly rock and then has a tiny little atmosphere, people think that the atmosphere of a planet like Jupiter extends all the way down to its very center. And so there will be no moment when like all of the gas is stripped. I mean, when all of the gas is stripped from WASP-12b, it will be no more. So that's a great question, though. Thank you. Yeah, right next to you. Sorry. I was pointing right next to the.
Should have stayed up.
Sorry.
Gonna get a workout in. Over here. Sorry, part of my reach.
Apologies for making you run up here again. So my question is, does the radius at which the planet is ripped apart, is that changed at all by whether or not it's a gas planet versus a solid planet? Like, because I imagine the sort of tactile compressive forces of a solid planet might keep it together maybe a little bit longer than the gas planets do. So is there any like data on how that affects the distances, or is it not really significant when it comes to that strong of a force?
Yeah, no, you're absolutely right. So the question was about whether what a planet is made of determines where its tidal disruption radius is. And it absolutely does impact it. So if something is made up of rock, then it's going to have these tensile forces. Like rock is pretty strong. It takes some energy to smash it. It takes some energy to pull it apart. It would take a lot of energy to pull it apart. And so if you have rock, that is going to want to stay together for longer than something like just a big ball of gas. And so the disruption radius of a rocky planet would be smaller than the disruption radius of a gaseous planet for exactly that reason, because the rock sort of holds itself together for longer. And that's something that we can model. I don't think it's something that we've necessarily been able to observe to any extent, but that's definitely something that we model with computer simulations, and I think has actually been modeled with pen and paper since the 1800s, which is pretty neat. But yeah, great question. Yeah.
How can I get this to you? Excuse me. Sorry. Can you pass that over? Thank you.
Hello. So my question is, would the pull of like the moon on the Earth have any effect on plate tectonics? If it's pulling that strongly, or over time, would it do anything with like under the surface of the Earth, so just like the water on top?
Yeah, that's a fantastic question. I'm far from a geophysicist, so I'm not sure about the Earth in particular. I can say that in terms of like geological implications of tides, there's a moon around Jupiter that has an orbit that is not a perfect circle. And so it's a little bit elliptical, like some of the orbits I was showing later in the talk. And as it goes around that orbit, it's at times closer to Jupiter and it's at times further from Jupiter. And so when it's closer to Jupiter, the tides that are raised on it are stronger. And when it's further, the tides that are raised on it are weaker. And so going between these very strong tides and weak tides at different points in its orbit, and doing that over and over again, means that it's constantly being sort of like stretched and compressed and stretched and compressed over time. And that causes there to be a lot of heat on the inside of that moon. And so that actually causes there to be volcanoes. That causes that moon to be geologically active in a way that it wouldn't otherwise be. So I would imagine that there's some influence on plate tectonics on Earth. I'm not entirely sure what they would be, but that's a great question. Yeah, got a question up in the back there.
Where? Okay.
Up top.
Gonna go around here.
Thanks. I was going to ask, with the rising sea level and the moon moving further from the Earth, is there any correlation, or is that accelerating?
So is the rising sea level accelerating because of the moon moving? Sorry.
No, the other way around. With the sea level rising from the ice caps melting, does that is there any correlation or any studies on the moon moving further from the Earth as a result? Because it's more tide.
Yeah, that's a great question. So the rise in the sea levels would not change sort of the overall radius of the Earth. And so it wouldn't change how big that bulge that gets raised is. So it wouldn't change how quickly the moon is moving away from us. But that's a really good question. Thanks. Yeah, right there in the blue.
In the case of that one star that sort of got ripped apart from the R star and it was orbiting around the black hole, I noticed it gets orbiting really close.
Yeah.
So is it also possible that it can get close enough to be ripped apart from the black hole?
Yes. Yes, it is. So the question was about this animation is not going to show up well with the lights on, but the star in this simulation that ends up bound to the black hole, that ends up on an orbit around the black hole, that comes very close to the black hole again. And the question is, will that eventually get ripped up by the black hole's tidal gravity? And it could. There would be some instances of this sort of binary disruption where the binary went close enough in the first place to the black hole to actually tear apart the stars themselves rather than just tearing the two stars away from each other. In this particular simulation, I think the closest they get is not close enough to do that. But if that orbit around the black hole gets changed by interactions with other stars, then it can definitely be brought down to a separation where it would be torn apart by the tidal forces of the black hole. And when that happens, that's what's known as a tidal disruption event. And that's a commonly observed class of phenomenon. You might also hear it referred to as spaghettification because the star gets sort of ripped apart like spaghetti by the tidal gravity of the black hole. So that's a very good question.
We have time for one more question.
Okay, I see a hand way up there.
Thank you.
Does the one star that gets flung off,
Yeah.
does it eventually start to slow down in any even nominal way? And can it get sucked into the gravitational pull of something else, like another galaxy or another star or anything, and get recoupled?
Yeah, that is a great question. And I'm trying to get it to go again, because if you watch after it gets ejected, the ticker that shows the speed of the star, you'll see that speed starts off at like 10,000 kilometers a second and then slows down to something like 4,000 kilometers a second. So it is being slowed down. So right now it's at like 10,000 and now it's going to tick down gradually and it's going to settle into something that's like 3,800 kilometers a second. It's being slowed down by the gravity of the black hole, and it'll continue to be slowed down by the gravity of the rest of the galaxy. And there are thoughts that some of the very fast stars that we see in our galaxy have actually come from another galaxy. They came from something known as the Large Magellanic Cloud, which is a small galaxy that's near to the Milky Way. There are thoughts that some of the very fast stars are exactly what you're describing, which are stars that were kicked out of that and kicked into our galaxy and then captured by the gravity of our galaxy. So great question.
Okay, so let's thank Mark one more time for his great talk.